In this video, we're going to take our first steps for the mathematical analysis of the mass spring system. We already saw the scenario where we have a mass attached to a spring that's at some or has some equilibrium position, but we are going to stretch that out or compress it, and we're trying to predict what the resulting behavior is of the spring and mass system once we let it go. And again, we saw that we should be able to predict this if we know what the spring constant K is and we know the mass, because there's nothing else we should need to know. And yet we need some other tool to connect the force diagram or the free body diagram to the mathematics and to a prediction. So how are we going to do that? Well, we are going to take ye old second law here, second law of motion, F equals ma, and build out some math for it. The only force that we have is our spring force, and it is equal to negative kx. X is our position over time, so it's a function. And what this is telling us is that negative kx is going to equal mass times acceleration. Fair enough. Well, what can we do with that? What's acceleration? Well, acceleration of what? Oh, acceleration of the block relative to its position. So that is the second derivative of our position. A is equal to the second derivative of position. And presto, we have a differential equation, because we have an equation, obviously, x is involved, with an equal sign joining them together, but we have an unknown function x, and again, it's a function x. We can't just solve for it as a number, it has to be a function. And it also involves the derivatives of x. X double prime derivative. So more typically this gets written out in a new form, but right now we actually have everything we need. We are looking for a function which, when we differentiate it twice, kind of equals itself, but with some constants. Actually, let's focus on that. Let's isolate the x double prime part. Move it to the left, and we'll divide through by m. And so what we're looking for as a solution is x of t that satisfies that equation, or, in a more meta sense, x of t that predicts the motion of the mass So what's going to happen to this mass when we let it go, subject to Newton's laws? Before Newton's laws, we would have no tools to do this. But now we do have F equals ma, and that's going to lock down the kinds of motion and the kinds of behaviors we will see from this kind of system. All right. As with any good analysis problem, it's easier if we simplify our coefficients so we don't have it too general to start. Then we can work our way backwards to the general case. If we make k and m 1, let's just go back a step here. Well, if k and m are 1, then it's just minus x on the right-hand side. That's it. We often leave out the bracket t's when we're writing the functions x and their derivatives, simply because it just complicates the view, but if you want to write them in, that's fine. So this could be or x double prime as a function of time equals negative x as a function of time, if that's a good reminder for you. And then we can turn it to a mathematical question. What function, x, when I differentiate it twice, gets me back to x itself, but with a negative sign? Some function I differentiate twice, I get back to its original function again, except with a negative coefficient. And hopefully you're yelling at the screen right now, x of t is sine of t, or if you like, x of t equals cos of t. Absolutely. If you're yelling something like x of t equals e to the negative t, I'd have to say a hard no to that one. If you differentiate it twice, if you differentiate it once, you're good. You get a negative sign. But if you differentiate it twice, you're going to have two negative signs, and those are going to cancel. And you're going to get positive e to the negative t, which is just positive x. So that one won't work so well. Give it an official x there. But sine and cosine, absolutely. Differentiate them twice, you're good to go. You do get negative of the original function. wait a minute. Again, think of the scenario. We're talking about oscillating masses. Well, of course, yeah, sine and cosine seem like perfectly normal things to describe a motion that repeats itself over time with some kind of period, and if there's no friction, some kind of constant amplitude oscillation. So we shouldn't be shocked that we're getting sines and cosines out of this. And even better, we can juice this up a little bit with the inclusion now of the masses and the k's. So if we rewrite this as x double prime equals negative k over m times x, what we might guess is, well, let's pick cosine. We're going to explore the full range of solutions as we go, but let's say we just pick cosine. And if we just put a t in here, then that doesn't work out. We just saw what that does. If I have just cos t and I differentiate twice, I just get negative of cos t. What if I slid a multiplier in? Oh yeah. In fact, one answer might be k over m. I'm just going to point back to an earlier example we did where we had x double prime equals negative 36x. And the solution for that one was cos of 6t. That was an earlier video. Why was it just a 6 when the multiplier was 36? Remember, every time we differentiate, we get one of these 6 popping out, and we are differentiating twice. So think about the other direction. If someone had said, oh, I need a 36 multiplier, I should put the square root of 36 inside my brackets here. So we're going to try that. Square root of k over m times t. Oh, okay, that's a lovely inspired guess, but it's not a guess. It's actually built on previous structure. But how do we know it's true? How do we know it's true? We check it. How do we check it? We sub in our proposed x of t into the equation, and we check if the left-hand side equals the right-hand side. That's it. How do we know something satisfies an equation? Well, we plug it in and both sides are still equal. That means it satisfies it. So the right-hand side is pretty easy. We'll do it last. The second derivative in the left-hand side is a bit more complicated. That means we need x double prime. Well, how do we get to that? We take derivatives of our solution. Our solution was x of t equals cos square root blah, blah, blah. We take one derivative. We're going to get negative sine of the same thing, square root of k over m. Trying to make these as legible as possible here, times t. And then because of the chain rule, we're going to get a multiplier of k over m square rooted. And then x double prime is going to equal negative cos, derivative sine is cos. The same thing inside, square root of k over mt. We're going to get another multiplier out of square root of k over m. And then this one that was already there is going to be copied down, and you can see where that's going. Two things multiplied that are square rooted. We get negative k over m without the square root altogether, cos of square root of k over mt. Square root only applies to the k over m part, not the t. So that's our left-hand side of our equation, actually. One's left-hand side is equal to x double prime, and that equals all this. Compare and contrast with the right-hand side of equation 1. Well, that's equal to negative k over mx. And we just said x was, what did we say x was? X was cos of square root of k over mt. And lo and behold, that is exactly equal to that. Those are equal, exclamation mark, exclamation mark. So we do have a solution to our differential equation. Through looking at some concrete examples, we had an inspiration for how the solution might look, and we can validate that by checking our guess against the actual equation itself. But that's not the entire thing. I mean, we found a solution, but we also could note that everything we just did would have applied just as well to x of t equals sine of square root of k over m times t as well. If you went through the same process, you would find that it too satisfies the equation. And it actually turns out that if we start with x of t equals, let's say, negative 30 times cos f square root k over mt, that would also work fine. If you think of the impact of some multiplier in here, it's going to multiply x. It's going to make this x bigger, but the derivative is also going to have that negative 30 in it as well, so it's not going to change anything about the left-hand side equaling the right-hand side. So that leads us to a thought or a plan for identifying the most general family of solutions. So I think we can actually make this broader and say, as long as I have a cos of square root of k over m and a t, and maybe I add, because we can add functions safely and not change their derivatives or not affect how derivatives work, we can do that, and then I'm going to put even some number in here, some constant. As long as it doesn't depend on t, it can be negative 30, it can be pi, it can be 500, whatever, and also some other constant in front of the sign. So some combination of sines and cosines, which I can't resist. You're going to be doing this all the time in APSC 174 linear algebra. This is called a linear combination. A linear combination of the two functions cos of square root of k over mt and sine of square root of k over mt. Don't sweat that for now. We're going to come back to it, but in any differential equation course you take later on, this idea of a linear combination is going to be huge. Oh, so much good stuff there. But for now, as long as you recognize that cos is a solution, sine's a solution, and if I added them together and multiplied them by scalars, that wouldn't really change anything. It would still satisfy this equation because the equation's so simple. If you can buy into that, you're ready to go.